The divergence theorem allows you to relate a surface integral to a volume integral. It's the final component of like the set of theorems that allow you to turn an integral of one type into an integral of another type. You had the, or not even necessarily an integral, but like a relation between functions. So the fundamental theorem of integral calculus was your first intro to this, that said that the integral of a function depends only on the behavior at the boundaries of the function, meaning an interval. Then we had the fundamental theorem of line integrals, which basically said the same thing, except on a curve. Then we had Green's theorem, which related a double integral over a two-dimensional region to an integral around the boundary of that region. Then we had Stokes's theorem, which related the behavior of the function over an entire surface to the integral over just the boundary of that surface. The divergence theorem is the final of these, and it says that if S is a closed surface, then this flux integral is equal to the integral over the region enclosed by the surface. And see how on the left-hand side, we've got an integral that we would usually call like a vector integral. That's vector calculus because there's a vector involved, there's a dot product. But on the left-hand side, I'm sorry, on the right-hand side, we've got the integral of the divergence of a vector field, which is itself a scalar. And so that ends up being a scalar integral, triple integral, which can be tricky, but not a big deal. We are going to be calculating this to simplify these surface integrals. Now, if you're anything like me, you see this and you start to sweat because hyperboloid is a big word, it's scary. And so hopefully this is going to be one of those things where the conditions of the divergence theorem allow this to get much easier, and it will. Watch what happens when you take the divergence of this vector field. The divergence of a vector field in general is the partial derivative of p with respect to x plus the partial derivative of q with respect to y plus the partial derivative of r with respect to z. And when you take these, like it does turn it into a scalar field. Remember that the p, the q, and the r are this. This is p, this is q, and this is r. So this is not really that hard because all of those are just polynomials. The partial derivative of the p with respect to x is going to be 3x squared y. We've taken care of that. Plus partial derivative of q with respect to y. That's going to be 2x squared y. See anything you like? Except remember it's minus because of this. So this will be minus 2x squared y. And so far they're like terms. Now we've taken care of this one. When we take the partial derivative of this with respect to z, the z is going to go away because x and y are constants, and it will be minus x squared y. The divergence consists of these three, which are all like terms. And the news gets even better because guess what 3 minus 2 minus 1 is? It's 0. So then the divergence is identically 0. So yeah, its integral must be 0. So in this case, the divergence and therefore the original surface integral must be 0, which is way, way easier than going through the big muck of calculating that surface integral. We'll do some more tough ones, like getting a little bit tougher and then getting a lot harder in the next couple of videos.